I do have two questions, if I may.
Okay, yeah.
Yeah. Is it possible to check the connection between core pipe and jacketing pipe constructed with A, cap, or B, round plate?
I don't believe so, but maybe that'll be better to... Tony, are you there?
Hello, yes.
Hello,
oh, okay.
So
Yeah, the answer to that is no. Right now what FEATools does is check all of the standard components in Appendix D. And so if it's not in Appendix D, then it's not available to be automatically inserted. And of course, the core to jacket pipe connection isn't something that you find in Appendix D.
Mm-hmm. Okay, thanks, Tony. Thank you. There was another question, Janine?
Yes.
Yeah.
Is it possible in special cases to get a higher code stress pipe using FEATools against V31 procedure, or is that out of question?
If I understand the question correctly, then yes, the possibility of the stress increasing using the FEA data compared to the 0702, compared to the B31 data, then yes, that is certainly possible to see the stress as it increase, yeah.
Yeah, I would say absolutely. In fact, in the case where you've got torsional stresses about a branch connection, B31.3 right now uses a value of 1 for the stress intensification factor. And in general, the stress intensification factor is closer to IO, or the out-of-plane stress intensification factor, times the D over D ratios. So the torsional stress intensification factors, as Chris showed earlier, can be off by 6 or 7 times for large D over T branch connections.
Okay, so thank you again, Tony. Is there any, that was the only questions, was it, Janine?
Yes, that's all I have right now.
Right, so let's go to part 3 of the agenda, which I have the agenda open here, is, well, performing the translation. Well, we're already doing that, and the criticality evaluation of the system. So let me introduce the criticality evaluator, because what you may want to do is just ask yourself, well, am I going to benefit? Is it worth running my system through this FEA translator? Will I get any benefits from doing this? And not every single system is, I guess, worth running through the translator. There are certain system characteristics which will have an effect. And let me, where is it? So let me just move these out of the way, because the translator is just finishing off the last intersection. So the question you may want to be asking yourself is, well, when should I use the translator then? And like I say, there are certain characteristics of your system which will have more of an effect on your or which will affect more how the more applicable data will affect your system. So these are things such as if your system has a high D over T ratio greater than around 50, I think is the number that we talk around. And does your system cycle? And you know, something greater than around 3,000 cycles. Notice that that 3,000 is, it's not set the 7,000 cycles as per the fatigue curves. It's, oh, what have I done there? 3,000 cycles. So it's not the full 7,000 cycles here that we're talking. But does your system cycle? Maybe if you have a low D over D ratio, something less than 0.4. Do you have high temperatures greater than, let's say, around 370 or so degrees? What T types do you have? The unreinforced fabricated Ts are, let's say we class these as the worst type of Ts versus a B16-9 welding T, which is, I think, what we class as, let's call it the best type of T. And do you have a tight system? We'll explain and look a little bit more about what we mean by a tight system in a minute. But if you have any one or more of these characteristics in your system, then you definitely want to be looking at FEATools and seeing the more applicable data that FEATools will provide. And FEATools provides the what's called we call it a criticality evaluator. And you can take all these characteristics, the high D over T, temperature, cycles, D over D ratio, your T types, and whether you have a tight system or not, and you can put these into the criticality calculator and run the evaluation, and the criticality evaluator will give a weighting to each of these characteristics of your system and run a criticality calculation to come up with a value at the end. And for example, the numbers that we've put in here are 15.2, so this is showing here as very sensitive. Here we are. So this is, if you come up with a criticality value of less than 5, then your system's not particularly sensitive for this more applicable data. You should maybe check local regions in the model, but typically this type of model is not particularly sensitive. Maybe you have a very flexible model with, I don't know, maybe just 4-inch straight T's, which the SIFs are the more accurate around that sort of size, because they would have been tested by Markle. If you have something between 5 and 10, then you have at least one single characteristics of your system that may result in sensitivity for the SIFs and the flexibility factors. Here you may consider running FEATools and just verifying that any critical values don't change. If you have a higher criticality values, maybe 10 to 15, then you have a number of, more than one property of your system that could result in it being sensitive, and you should really consider running FEATools and verifying that things are okay. And if you have something greater than 15, then you certainly should run FEATools definitely and verify that your critical values don't change. And because the criticality evaluator is so easy, then this will take you 3 or 4 seconds to perform. So one of the things I discussed was, do you consider your piping system as tight? Well, what do we mean by tight? Let's just explain that a little bit further. So here we have a very simple system here. There's a unreinforced fabricated T shown here at what we've called node number 30. And would we consider this system tight? Well, if you can have an estimate for the flexibility factors, just like we did with the in the previous example where we looked at the I and K calculator, you saw that took 2 or 3 seconds to run as well, then you don't necessarily need to use them in the analysis. Just decide that, is that going to have an effect? So with this system here, this geometry, this unreinforced fabricated T, the IK calculator comes out with these flexibility factors: 6.2 in plane, 1 out plane, and 14.7 torsional flexibility factor. Timesing that by the OD of the pipe, K times the OD, like we discussed earlier, this equates to an extra 3.7 in terms of the in-plane and 9 meters worth of pipe in the torsional direction. So as I say, that came from PRGIK calculator. Now, is 9 meters, that's as near as makes no difference, 9 meters of flexibility length going to change those loads on the pump nozzle at 40? Well, 9 meters is a reasonably significant amount of data amount of length, sorry, relative to the rest of your system. Around the T you have, well, 1.5, 2.5, 2.5, 6.5, 11. Here we've only got 13.5 meters of flexibility anyway in the whole system. On that 9 meters, that's almost the same amount of pipe length, flexibility length again. So that's relatively quite a significant amount. So it may well have more of an effect on the loads of the pump nozzle at node 40, and run the analysis. In fact, it does. The Y moment, for example, reduces by over 45%. So yes, that 9 meters of flexibility length, as we call it, does have an effect, because 9 meters is fairly significant compared to the overall. We've only got 13 or so meters of pipe anyway. And this is what we would call class as a tight system. But if you were to look at this, it's the same system, we've just increased the length of this pipe run and this pipe run. If you put the same T in this system, is that same 9 meters of flexibility length going to change the loads at the pump nozzle? Well, 9 meters is not as significant as it was before. We've got 15 and 17 and the rest, so we've got considerably more amount of pipe than we had before, so not going to have so much of an effect. This is what we would call a flexible system. So basically, where the amount of equivalent flexibility length is a significant proportion of your system, the area around that you're concerned with. If it is, then that would be a tight system. So let's now take a look at the criticality count or criticality evaluator. I can close that now. The criticality evaluator for our system itself. So the criticality evaluator is available from inside the translator window under the options menu, piping system criticality evaluator. And here we can fill in the information for our system that we're working with. Now I've already worked out what these values are, the max D over T ratio and so on. I've already figured these out. So the maximum D over T ratio is, well, at some location we have a 1400 by 5.6 mil pipe. So that's a 253 is our maximum system D over T ratio. That's a significant D over T ratio. It's very high. Remember, note 11 says B31 SIFs are only valid for up to 100. We're considerably above that. Now, what's the minimum D over D ratio? Well, there is a 1400 by 400 branch at some location in our system, so that's 0.286 is our minimum D over D ratio. This system, well, it does cycle, so we're going to say, let's just put 3000 in the number of thermal cycles, and same for the pressure cycles. This does cycle. And the temperature, well, this is, well, let me tick the metric button to go to metric. So our operating temperature is 205 degrees and the pressure is 0.4 megapascals. What types of T's do we have? Well, we do have some unreinforced T's. So that's the lowest rated T type is the unreinforced T's. You can see the different types of T's here. P16 welding T is the best, and unreinforced T is the worst. And we do have some unreinforced T's in this system. Is the piping system considered tight? Well, there are some tight areas in the system, so maybe we could tick that, but the whole system is not tight. However, we don't really need to tick that because, the other thing is, we know high thermal stress exists, so I can say I know the high thermal stress exists. And if I evaluate this without ticking the system is considered tight box, it may be, it may not be, then shift that to the side. The criticality count here is 27. That's very, very sensitive. The very sensitive cutoff point is 15, and we're considerably above 15. they're at 27. So this is very sensitive. The criticality evaluator gives us some notes on this. There are multiple characteristics in the system that can be impacted by more accurate analysis, and so on. And here we have a number of notes on what's happened here. The minimum D over D is less than 0.5. The SIFs for the run side of this branch connection may be grossly overestimated, referencing WRC 329. More applicable data should be used. So that's, I think, pretty conclusive. This system will certainly benefit from running the FEA translator and getting the more applicable data. So now, I'll close that down because by now, for those of you that are running the evaluation, or running the translation, sorry, who are doing the evaluation, I guess I was right, it should have finished by now, and you should say, well, the file has been successfully converted, and here we now have some output. We have text, graphical, and, well, chart and graphical output, rather, available to us now. So let's take a look at some of this data. Well, I'll start with the text output, and let's take a look. If you remember, let's go and find node number 180. So I'm just going to scroll down, and here we go, intersection node 180. So let me scroll down so that's at the top. So all this data here, oops, didn't mean to do that. There we go. All this data here is for node number intersection 180. And remember, that was where we had the failure in the sustained and expansion load case. Now, let's take a look at the stress intensification factors first of all. Here at node 80, node 180 rather, and in the sustained case we had a failure on the branch. And the branch intensification factors, we have the B31.3 and the FEA. Just going to skip back to the top there, sorry. Oh, I've lost one. Oh, here we go, 180. So, sorry, I found it again. For the in-plane and out-plane, we had number 16.8 and 22 intensification factors. For the FEA analysis, that in-plane, okay, the out-plane is fairly similar. The torsional's actually considerably more. It's 21 versus 1 for B31.3, significant difference there. And the in-plane intensification factor has dropped. It's 6.8 or 6.9, let's call it, for the in-plane. And also notice the difference in the run pipe SIFs. The run SIFs for B31.3, same as the branch SIFs, but for FEA we have 2.6, 0.5, so 1 for the outplane as opposed to 22, so considerable difference on the run pipe. A rather large reduction there. So we have considerably lower, it's about a 40% reduction, or it's reduced to around 40% of the original B31.3 SIF for the in-plane intensification factor. And let's take a look quickly at the other problem we had, which was node 2110. I think I saw that. Yeah, here we go, 2110. Here we had a problem, and well, the problem at 2110 was on the run pipe, the header pipe, and again we had large SIFs here, 15 and 20, there or thereabouts. These have now dropped to 8 and 3. So the in-plane SIF is not far off half the original SIF, and the out-plane SIF is it's only about 18% of the original. So these reductions in SIFs should make quite a bit of a difference to the sustained load case, which was failing due to, we believe, the high intensification factors. And then also we had quite a few problems for the expansion load case. Let's look at the expansion load case. So let's just look at the worst locations here. The worst failure was in fact at node 210. So let me go to the graphical output. Here we can take a look also at graphics. So you see we have graphical representation, and you can choose which intersection you're concerned with. Node 210 was the worst location. The overstress was on the branch. So let me go to node 210 branch. Let's see. So node 210 was one of the laterals. The lateral has now been converted to a finite element model. The analysis is run. Okay, here we're looking at the pressure SIF, which is quite high. But the main problem, this was the expansion case, so the main problem we're concerned with is the flexibility. We just want to add more flexibility because the problem is to do with our expansion. So let me go back to node 2, or was it node 210? Sorry. I think I saw node 210 as well. So I'm just looking for node 210. No, it's not in there. Here we go, node 210. Well, we have some flexibilities here, and let's take a look at, you can see the difference between, in terms of the stiffnesses on the branch, which is where the worst problem was in terms of the expansion load case. We have some significant flexibility here. According to B31.3, axial, in-plane, out-plane, and torsional are all rigid. FEA, we've got some stiffnesses here, and we've got a considerable amount of flexibility in the axial direction. Very, pretty low stiffness there. We've also got some. These numbers are significantly less than rigid, so there is quite some flexibility here. And if I go to, instead of looking at the stiffnesses, we have the flexibility factors, which will be more helpful here. So here we have the flexibility factors that will be used, or that we can use to see how much flexibility in terms of equivalent pipe length we would get. The outplane flexibility factor, well, that's 80, the third one. So it's axial, in-plane, outplane, torsional. The outplane rather is 80. That would give us a lot of flexibility. Well, it's 400mm pipe, so 80 times 400 is around 32 meters worth of extra pipe. That's quite a lot of extra flexibility length. So we have quite a significant amount of flexibility here at node number 210, which was where our worst failure was. I mean, we could go and look at the rest of the, go and look at the rest of the nodes that were causing us a problem, but I'm focusing on this one because this was the worst location. And just before we break for questions, I'm just going to go to the chart output, and you can see here this gives us a chart output, gives us an easy to read comparison between the B31.3 intensification factors compared to 0702 and the actual FEA analysis where available. So okay, we only have FEA for the axial SIFs, but for the in-plane and out-plane SIFs, we have FEA, which is clearly, you can see that's the blue line, orange 0702, red B31. And here you can see, well, generally 0702 tends to correlate fairly well with the FEA line, but B31 can be quite a way out. For example, the in-plane SIF, well, this first intersection, that is quite considerably over-conservative, You know, we're talking, what's that? That's around 16, 17 according to B31, when FEA says it's around 6 or so. So B31, very, very conservative at this particular intersection in terms of the SIFs. But, for example, the outplane, say this location here, let's look number 6, B31 is actually quite a way below the FEA results. It's, well, I can't quite read what that is. It's a little bit small in this size window, but it's, I don't know, it's around 10 or 12, I guess. Whereas it's getting on for around 20 in FEA, so non-conservative at some locations for B31. So our more applicable data will be very, very useful. Now, in addition to all of this chart and text data and the graphical output that we can look through, we've also got a new CAESAR II file that's being created, and that will be our next stage to review that new CAESAR II file. But first, let's break to see if there are any questions. Janine, is there any questions?
Yes, I do have some questions.
Okay.
Let me start. So I think it wasn't clear earlier, so I kind of asked that question again, if it will be done in the future time to check the connection between core pipe and jacketing pipe.
Okay, so yeah, we can't do it now, but will we, or will that be incorporated in the future then?
Okay.
Okay. So yeah, Tony would be the best to answer that, of course.
That's an interesting question. That's the first time we've ever asked for those particular connections, and so I mean, in the future is a long time, and so at some point in the future, absolutely, I would say any areas of discontinuity we're certainly interested in. So those are definitely areas of discontinuity for us. Hillside connections, connections in heads. Y pieces, large block fittings, those are some of the more common fittings that we're looking at for incorporating in FEA tools in the nearer future, let's say.
Okay, thank you. And is the FEA calculation carried out for the whole pipe system or individual only for every T section?
Yes, individually for every intersection. And then the results of the FEA, the flexibilities and the intensification factors are passed back to CAESAR II in the form of a new model with those incorporated in at the appropriate locations, which we'll take a look at in a minute.
Okay. And if the ZIFs, which are calculated by FEA tools, are greater than B31.3, is it allowed to continue using values from B31.3? In other words, is it allowed to use mixed values from B31.3 and FEA tools?
No, you can't really mix and match to see what suits you. If you're using the more applicable data and it does happen to be greater than B31.3, which it can do, then you can't discount that and go back to B31.3. That would be, I was going to say wrong, maybe that's not the right word, but certainly no, you wouldn't be able to just mix and match and choose what would suit you the best.
Although I would add, at the end of the day, it is the user's responsibility.
Yeah.
And so if for some reason he feels that a B31.3 is more applicable for whatever reason, the B31.3 code tasks the designer with making that determination.
Yeah. Okay. Yeah, let me re-clarify my position. Then I wouldn't mix and match. But yeah, like Tony says, it's the user's responsibility at the end of the day.
Okay, thank you. That was it from my side.
Okay. Okay, so is everybody happy for me to continue on? the people who are following, I know they're all muted, aren't they, all the attendees? But I would just ask now.
Yes, they are.
Yeah, I suppose maybe I should have asked this earlier on. But for those who are following that do have the software, is everybody following okay with this in terms of performing it in the software themselves? I guess you would have let me know if you had any complaints come up on your in the chat, Janine.
Yeah, pretty sure I would.
Yeah.
Yeah. No complaints yet.
Okay. Okay. So let me continue on then, and as well as all this data that we looked at before the question break, which I'm now going to close, I also have a new CAESAR II file. So I'm going to go back to CAESAR II and open the new file. Same name, just with FEA appended to the end of it, because that's what I said to call it. And I'll go to piping inputs. So first thing I'm going to do is I'm going to increase the size of my restraints because they were a little bit small. And the first thing you will notice when you go back into CAESAR II and reopen your file is you have a lot of these restraints here, which I don't even know what colour you'd call this, beige colour restraints. A lot of these dotted around at every intersection that we have. These are the, and if you remember to my PowerPoint, these are these CAESAR II node and C-node pair with a stiffness. So that's what these restraints are. These are representing the stiffnesses that, of course, were calculated and came from the FEA analysis. So what the translator's done, of course, you saw it calculated all these flexibilities and so on. And the new CIFs, it's going to apply these into CAESAR II. So let's take a look at where was 180. Here was 180. So at 180, where previously the CIFs were, I forget what they were. What were they about? 16 and 18, I think they were, on the branch, because that's where our failure was. And it's a little bit difficult because of the, for me to select the actual point that I want because of the. So I'm just trying to select. There we go. Got it. So I think I'm looking at the right location here. Maybe it's better if I just go to the CIFs spreadsheet. Here. So what am I looking at? 180. Here we are. This is what I was looking for. So just get back to the PowerPoint. See, the translator has turned the T's, which were like so, model like so, flexibility factor of 1, CIFs applied at the centerline intersection. We've converted to this model here with the flexibilities that we saw and also the new CIFs. So we've got CIFs applied at B, which are the branch CIFs here, which is what I'm looking at. This is now node 184 to, well, 3000 is the bend. That was the bend previously. Just hide that. So 3000 is the bend up here. So 184 to 3000, which I was clicking on the right one. That was just me, user error. So these are the new CIFs anyway. 6.8 and 20, whereas before they were 16.8 and 22. If you remember, I'm looking at these. I've got them written down in front of me. But according to B31.3, these were 16.8 and 22. Now we've got 6.8 and 20. So a drop in CIFs, quite a significant drop in the in-plane intensification factor. In addition, we've also got some flexibilities. Let me go to the restraints spreadsheet.
Tell you, Stephen, that tends to be common for laterals where the in-plane footprint is quite a bit larger in a lateral case than it is for a normal intersection case. You simply got more pipe resisting the bending moment.
Mm-hmm. Yeah, okay, yeah, I understand. And of course laterals are something that just aren't covered very well by the Appendix D, for example.
At all, right.
Yeah. So this is certainly more applicable data. There's no question on that for this. Now what we've also got is these restraints here. I've just popped up the restraints spreadsheet, and these are all the restraints. There's a number of restraints at all these intersections, all with a stiffness applied. Well, a lot of them rather, with a stiffness applied, which was that stiffness as was calculated during the FEA run that we saw in the text and the graphical results. These have all been applied as appropriate, with, as you've seen, no input on my part. It's all handled by the software, so that saved me a lot of time, and I've got a much more accurate model. Now what I'm going to do is I'm just going to turn off this and hide all the restraints with C nodes, just so I can see a little bit better what's actually going on. And let me go to translucent mode, and this is what I was going to show, just to see how the, if I go to the side view, it's just to see how the model has changed. So if I can put node numbers on it, yep, it's not crowding it too much. So once again, this is just me reiterating that instead of this type of setup, rather, this is what we actually do have. So and this, and I don't know if this is going to make it. Okay, so yeah, it's a little bit difficult to actually see, but you can see we have a number of restraints with C nodes, with the stiffnesses, and this has turned in from the center of the header to the wall. We have a rigid element, the SIF applied appropriately on the branch connection, and we also have the SIFs applied correctly either side of on the header, and the flexibilities as well, which obscures it a little bit, but there we can just about see, I think, in the graphics where the restraints have been applied. So in terms of user involvement, very, very, very easy for me to do. And what's left for me to do is I'm just going to run the analysis. I'm just going to do a batch run, quickly run the analysis. Of course, everything else is exactly the same as before. The only difference is our model is now more accurate. Just take a few seconds to run. And, well, first thing you see, oh look, we've got no red text anymore. So let me go and look at the stresses. And if you remember node 180, now 2010, they were the highest stress locations. Well, these are now these two locations here, 2114 and 184, with the node numberings of course changing slightly because of the updated model. But now using the more accurate SIFs, 6 instead of 16 or whatever it was, we've got lower stresses. Everything's now acceptable because of the more accurate SIFs in terms of the sustained case. And in terms of the expansion case, we've got lower stress. It's 194, whereas before it was, I forget, but it was overstressed. I remember that much. I just can't quite remember what the ratio was for the expansion case. But anyway, suffice to say, it was overstressed. It's now no longer overstressed. It's 94%. Because we've got that added flexibility that we didn't have included in the model before, but of course it was always there because the intersections are inherently flexible. They're not rigid connections or rigid components like the Appendix D tells us to specify. So the more applicable data given us the flexibility, and now we are no longer overstressed, even though in some cases we do have higher SIFs. Now, instead of me trying to compare between the old original model and the new FEA model by looking at the reports in CAESAR II, FEATools also includes a tool, a comparison tool, just to make this comparison before and after a little easier. Under the options menu again in the translator window, go to the file comparisons. This allows me to add two or more. Sorry, I'm just trying to browse for the files as well. This allows me to select 2 or more CAESAR II files. I've only got 2, so I only need to select 2 here. And compare the results. So I'm just checking everything. The display units, you can choose your units. I've got making sure mine are all in metric. And compare the resultant displacement, forces and moments as well. And turn the filter off for now. And that's it. Just select the 2 files, make sure your units are correct, and hit compare. And I've still got the file open, so you can't open the results file. So let me try that again with the file closed. Works a little bit better. And here we have the 2 comparisons, and it's taken the results from the 2 files that I've selected, compared them and plotted them with a chart. So just a quick overview of what these are. We can see some differences here, and let's see which are. I'm just trying to see where I noted down which were the better plots to look at. So first we've got displacement, restraint loads, forces and moments, global forces and moments, and the code stresses as well. And let's look at the, well here, this is, first of all, this is the displacements report. You can see the original model in blue, the new model in orange, and the differences between the displacements. The second chart on the right hand side is the same plot, or the same data, just ordered by the maximum difference first. But I'm going to go straight to the stress, this one here, the code stress plot, because that's what I've been focusing. I've been focusing on stress, so this is what we're looking at here. Now, because node numbers may differ between the 2 models, each node is given a node index value, and you can use the table below or the tooltips to determine what node index refers to the actual node. Excuse me. So this chart here tells me that, well, let me look at the right hand side chart. That is the ordered chart, ordered with the biggest difference first, and that shows me, well, the biggest difference here in load case 5 at node number 2050 we've got a drop from 120 megapascals down to 74 megapascals. That was the biggest change here, and that was at node number 2050, difference of 46 megapascals. So that was our biggest difference here. And this chart shows that most of the locations have dropped in stress. You can see there are a few locations where, here for example, we've got an increase in stress. But as a whole, or on the whole, most of the locations have reduced in terms of the stress, as you can see from the chart and also the table below the chart. Now there's similar charts for all of the displacements, restraints, and they all work in the same way, and all compare, by default at least, all the load cases. But if you're concerned with a particular load case, so see here I've got some results from load case 3, some from load case 5. It's maybe you want to concern yourself with just one load case. So I know load case 5. I can actually click this descriptions button to see what my cases are. Excuse me. But I know load case 5 is my expansion case, and that was where I kind of had more problems. So maybe I want to filter. You can do it on nodes as well. If you're concerned with only a certain range of nodes or load cases, you can filter on either or. So let me filter, tick the filter, and say I want to look at load case number 5. That's where I had my problems. That's the only one I'm really concerned with at this precise moment. Rerun the comparison, and here I have my data just for load case 5. So here I can see that pretty much every single node has dropped in terms of stress in the expansion case, case 5. So here we've seen that adding the more accurate flexibility factors and SIFs has decreased the stress, and it's dropped the stress enough for us to move from being overstressed to no longer being overstressed. And from what we've seen, and maybe Tony can confirm or deny this, but from what we've seen is this: most of the time this is what you're going to see. The correct SIFs and Ks are helping you and do tend to work in your favor, but like we've discussed already, this is not always the case. Don't forget that some of the SIFs can be non-conservative. If we put SIFs and flexibilities which are conservative in the model, then it might end up increasing the stresses. And also things such as like Tony mentioned, the torsional intensification factors, including those, which is where currently they're 1 in B31.3. If we include an accurate torsional intensification factor, then that could also cause things to not necessarily work in your favor. But I think you would still want to know, even if things weren't working in your favor, you still want to know if you have an increase in stress or force or moment or something with the more accurate data. So I think that is everything I was planning on showing. So are there any questions, Janine? I think I'm done with the exercise. I'm completed. So are there any questions, Janine? Janine? Guido?
Oh, sorry, I was still on mute.
Okay.
Yes, there are questions. First one is, would it be a sensible option if individual branches could be selected in the program for FE analysis?
And the answer to that is yes. It's reasonable. The problem is that flexibilities tend to be uniformly distributed throughout systems. Now that's generally true. In specific cases it may not be true. It was when we started to set this up, we looked at allowing users to pick individual branches. It added complexity to the process, and so the final decision was to just make the conversion for all the branch connections, store them in the library, and then the next time the user makes the run, the data is pulled from a library and the conversion is almost instantaneous. So very quickly going through the process of selecting individual T's, it wasn't very helpful anymore. And so we pressed the convert button, all of them are translated, and that became the easiest approach for us to take, and so that's what ended up in the tool.
And what kind of flexibility will be used in the FEA model from center of pipe to the branch, so from A to B? Is this the stiffness from the run of pipe, or stiffness of 1E, 1O, or anything like that?
Well, this is, we're asking, the green stick here, what will be the stiffness of this, I think is the question that we're asking. And in the model that I have run, this is rigid. But I'm going to, again, I'm going to maybe ask Tony to come in on this, because this can I believe this can vary depending on the geometry.
That's right.
I know we have a document on that.
It varies as a function of the D over D ratio. When the D over D ratio is greater than 0.5, a stiffness is inserted there that's proportional to the run pipe. And the reason for that is so that the stress intensification factors can be calculated both at the branch surface and at the intersection point.
So it varies based on the D over D ratio, I think is right. the basic answer, Janine.
Okay.
And that's in line with Section 3. That's the approach that Section 3 takes for flexibility application to the piping system.
Okay, thank you. Could you also make the transferred CAESAR II model available for downloading it?
Yes, we can sort that out. I guess Guido will be sorting that out. I think he's uploading things to the ICAS community. So yeah, we can certainly supply the translated model, no problem.
Perfect. And then one last question: is it possible to include also the EN13480 code values for comparison the branch connections?
I would say yes. We think that's a great, that would be a great feature to add. They're very similar oftentimes to the B31.3 CIF values. And so I think that's something that we definitely want to look to doing in the future, just as soon as is practical in the next development cycle.
Excellent.
Yeah, that was all the questions I had.
Okay, great. Just before, well, just one thing, and Tony did mention this earlier, that once you've, and I think I talked about it as well, once you've run an intersection type once, then that intersection type is available in the library. The second time you run any model with that same intersection in, then the FEA is not needed. FEATools can obtain the results from the previous run. So I'm just going to convert the same model as before and it took a couple of seconds to convert the model the second time. So that's what we were talking about with the FEA run. Takes, around about, we see around a minute or so per intersection as an average value. For the first run, any subsequent runs on the same type of intersection, you saw then it was instantaneous. So I just wanted to show that, how quick it was the second time I ran the same model. So sorry I interrupted you there, Janine.
No, not to worry. I just got another question.
Yeah.
Tony said FEATools is working for connections according Appendix D. 45-degree connections are not in this appendix per standard, but it works. Will it also work for epsilon connections?
Could you repeat the description? What type of connections, Janine?
Well, yeah, I didn't.
Y connections? No, is that epsilon?
Y connection.
Not at this time.
Okay, thank you, Tony. Yeah, I don't have any more questions.
Okay. I guess while you're here and we have your expertise, do you have anything to add, Tony, to what I've been through over the past hour or two?
No, Steve, I think you made a great presentation. I would emphasize the comparison tool. We surprisingly use it more than we use the FEATools translator because it's so good comparing one CAESAR run to another CAESAR run. The typical design process, of course, is changing restraints or modifying the piping system a little bit. And if you've got more than a dozen or so load cases, it's oftentimes difficult to tell if you've made an impact on particular load cases. And so the comparison tool goes out and scans all the load cases and all the nodes and shows us the largest differences.
Yeah.
So it ended up being just a very convenient tool for comparing 4, 5, 6, 10 different versions of CAESAR models to see which ones had the lower pump loads or the lower support loads, for example.
Yeah, because of course the comparison tool, they don't have to be a before and after translated tool. Sorry, translated files. They can just be any CAESAR II files.
Exactly.
At all. Yeah.
Yeah. And so the comparison tool and the PRGIK calculator are the tools here that we end up using the most, because as you pointed out, I think terrifically, Steve, what you really want to know about flexibilities is the K factor. And so you go into the PRGIK tools, check the K factors. If they're all low values, then there's no reason worrying about extra flexibility in the model.
Yeah, exactly. Okay, great. Guido, do you have anything more to add? Or ask or comment on or anything really? Is he there?
No, I don't think he's there.
No. Okay.
Ja, ich glaube, damit können wir das Webinar für heute beenden. Ich bedanke mich bei allen Teilnehmern. Ich hoffe, Ihre Fragen sind beantwortet worden. Falls nicht, kontaktieren Sie uns gerne mit weiteren Fragen, oder falls Sie die Evaluierungs-CD zu den FEA-Tools benötigen, können Sie sich auch gerne bei uns melden. Thanks to Chris and thanks to Tony for attending our webinar. Und ich wünsche allen einen schönen Nachmittag.
Okay, thank you everybody. Thank you for your time this morning. I hope it was useful to you. I'm sure it was. And we look forward to hearing from you. You can contact either, I think Guido displayed his email and Jörg's email at the start of the webinar. So you can speak to Guido and Jörg. Of course, they will be able to handle any questions in your local German language as well. I don't speak German, unfortunately. So, of course, you can always contact myself as well. It will just be in English.
Many thanks, Chris, for the great demonstration.
Okay, thank you, Jörg.
Yep, and thanks from Houston.
All right, thanks,
Thanks, Tony.
It's our pleasure.